from R. So we will show some examples. And also we'll show you how you can access the data in the EU map, the European data. We have a lot of data. So we will show how to access R. Let me see, this is the slides. Let me just share my screen. Share screen. So this is the last session of the day for the R training. As I said, it will be focused on computing with cloud alternatives. For those of you that are new to cloud alternatives, I think it's going to be especially interesting. It looks like, you know, it's just another GeoTIFF format, but as you will see, it's magical what you can do, and you will see that GeoTIFF basically becomes like a spatial database, so you can do queries, overlays without downloading terabytes of data. So I'm going to introduce you to that, and we will run a little demo. So we will do actually one from Africa. I have also demos for Europe, but I will just show you where they are so you can play. But I think the one from Africa, it's more interesting because we modeled basically distribution of agricultural, distribution of cropland for Ethiopia. And this is a very nice example that shows, you know, large data set, 1.5 terabyte that we subset and load in R and do processing. So cloud alternatives, how to use them. You can use them QGIS. So this one I just loaded. I will do it one more time. This is a Landsat image for Europe. And you see I can zoom in and we can see that image. You can see the values changing. And this image is not here locally on machine. This image is on a server, and we can load it and look at that image, and we can zoom anywhere around Europe, and we can also crop. We can crop just the window we saw. We can run analysis without downloading the data. So this is the one way to use it in cloud. Optimized GeoTIFF is directly in R. The other ways to use it, which is probably better, is to use the R and then combine Terra Package, Jiggle. So let's put this Terra Jiggle. So you can use Jiggle or Terra Package, and then also you can do spatial overlay in parallel. I will show you that. It's super important. Think about it when you have, let's say, 1,000 points, and you said, you guys, you have this cloud option GeoTIFF, maybe 10 terabyte. I don't want to download 10 terabyte. I just want the values on the 1,000 points. And then you want to parallelize. You can parallelize. We tested up to eight processes. So you can speed up 8 times to do spatial overlay. And then you get the values. And then you can do some data mining, modeling, and then you say from all these bands you have, I only need these 5 bands, and then you can download these bands, and then it's only, I don't know, maybe 10 gigabyte. So it's a very intelligent way to use the data. Last week we had a summer school, and Marius Appel, he made this package called Jiggle Cubes, also very fast, very efficient. And so he gave a talk, and he explained the cloud alternatives. There are 3 things about cloud alternatives. Number one, they have pyramids, so they are available in different scales, so they're already pre-cooked, aggregated. The second thing, they have tiles, so if you want to download, eventually just download a tile. And then the third thing is they are compressed, so they're internally compressed, so it's a very low bandwidth requirement, the lowest possible, to pass the data. And Cloud Options GeoTIFF works on HTTP requests. So basically, it works. We use HTTP to access data like in a geospatial database. And I'm a really raster person, by the way. So I don't believe in vector data except for the points and lines. But even lines, I will rasterize. I rasterize everything, especially polygons. I don't see any point in using polygons. So I'm a really raster person, especially now with the cloud optimized GeoTIFF. There's nothing comparable to vector data. They are building some solutions which are called flat GeoBuff. So they're building some solutions, but it's nothing that is as ready as the cloud optimized GeoTIFF. So we are going to talk about that, but as I said, you can watch this video, please, by Marius Appel last week. It's on our YouTube channel. We have also this tutorial, geospatial data tutorial, and if you look at that tutorial, you can see there's the example with the satellite data. So we have, as Carmelo mentioned, like 1,800 images, different bands. And these bands, they all have basically an address and also vectors. They are on the web feature service. So you can load all the point data, but you can also load these satellite images. So this is one band, for example. This is the Sentinel S2L2A product 2018. So going from the 25th of June 2018 to the 12th of September 2018. So it covers basically autumn, summer. It covers summer, so it's a summer band, and I can load it into QGIS, as you see here. So I can do it one more time. Wait, I will do it one more time. So I stop this one. I just do the same, or maybe I can add the other one, the Landsat. This one. So I can go to the layer, add layer, vector layer, raster layer, sorry. And then I just say instead of file, I say a protocol. So instead of file, I say protocol. And then I can add this Landsat. And then it will take a bit of time. When I say add, it takes a bit of time, about 2-3 seconds. So don't get discouraged with that. And then you can, now it's added. And now it's very dark, you see? It's very dark. So what I have to do, I have to I have to change the display. And I put usually, for example, 2 standard deviations. And then you see it goes from minus. So I have to put here 5. So I have to do some manual fixing because these are the actual raw values. And when I do that, here we go, we get a Landsat image. And you see it's a 30-meter resolution. I can turn off the Google on the back. So now it's just the image. And we can see actual pixels. And you see these are the, we clean up all the clouds, we clean up all the artifacts and fill in the gaps. All our images are about 98%, at least 98% pixels are available, except for some winter months that we have less than 98%, but otherwise we guarantee 98% pixels. So these are proper analysis ready data. The analysis ready that many companies call analysis ready, it's not analysis ready, by the way. Analysis ready when you don't have to do any cleaning, which is, and there's no gaps, it's complete, consistent, it's ready to go. So we made this data, which we now call analysis ready. And as you see, sometimes when I zoom in, it takes a bit of time, but you see, I don't download the whole image. My session shows that I'm downloading data, so there's here. And so I am downloading, so it's something like 7 megabytes per second, you see, when I move somewhere. So let me see if I can put this on top. Okay, view, always on top. So if I, let's go here. So now I'm looking at internet. This is always on top. So if I zoom somewhere here, you will see it will be downloading extra data. See, it's downloading extra data. There could be sometimes peak. If I zoom out, now again, it has to download. Now it downloads something like a 10 megabyte per second. And you see it takes time till I get the whole coverage. Yes, it takes some time, but it's a question of, let's say, 2 seconds. So if we had if we had bigger budget, we could have speed it up to put it in multiple data centers, and then anybody in the world. So then we'll be like a Google. Anybody in the world will get very quickly data. But otherwise, we are happy. We find this service to host the data at low cost, and it looks like it's working. It's good enough, and it allows people to access data remotely. So that's about Cloud OpenSGT GeoTIFF. Who's using it for the first time? How many people? That's great, fantastic, fantastic. So you see, I can show you we're accessing the data. It's kind of like a virtual layer, and it creates an illusion like we have the data locally on the machine. We load it in QGIS. You see, that's the layer, but we are just downloading a part of data, and this is this. First, you look at the scale that you look. So when this image we download, that's the aggregated value. So if I go to the QGIS and if I open this pyramid, you see we have pyramids. And so then when I zoom in, I pick up the scale. And then this is the HTTP request, goes to Cloud OpenSGT GeoTIFF. And GeoTIFF is just a single file on a server, just a single file. You can also split it, but usually single file. And then it looks, okay, you're this scale, and then picks up only that scale and picks up a subset that you need. And then you display. Okay, so it's a very intelligent system that helps people access very easily data. And then in this tutorial, we also explain, in the tutorial, you can get the points. You can take Switzerland, for example, get a shape file of Switzerland. And then you can match the Switzerland, let's say here somewhere, you can match the bounding box of Switzerland, and then you can crop that image, and then you say, I only need it for Switzerland data. And you can also use directly GDAL. That's also fantastic. You directly use a GDAL. So here I will increase the size of this just a second. Yeah. Okay. So this is the city of Amsterdam. So I can go to my RStudio. Let's see, open project. So I'll open this one. Neither one. I'll put just a new script and I'll increase the size a bit so you can read. Just a second. So I say tools. Can you read it a bit better? Yes, or I make it a bit bigger. Let me make still bigger. Something like this. Yeah. Better. You can see. Yeah. Maybe not 36. I can do only 24, 36. 36 is too much. Let's keep it like this. So what you see here, I can send to a command line. Well, we can start like this. We will start doing the GDAL info. So let me just see the version I have. So this is under my Windows. I have a version 3.1.2. So this is compatible with Cloud OpenSGT. The versions below, I think 3.0, they are not compatible. So they're not. You cannot use them efficiently. But this one is compatible. So what I do, I can do GDAL info, and I can ping. Basically, I ping this this Cloud OpenSGT GeoTIFF, And so what will happen here? I will basically, I will just go and find out about this layer, which is a virtual, it's a virtual layer. It's not locally derived, but it's on the HTTP. And I use this virtual server CURL query. Okay, so I have to specify in Jiggle info this thing, otherwise it wouldn't work. So that's a little tricks with the cloud.initiative. But you see, when I query it, when I get back, it doesn't go and download, but it just checks the file, and it gets kind of the header of the file. It's quite long, but I can see, okay, it's a pretty large image, 180,000 by 150,000. So it's the whole of Europe, 30 meter. And it has the coordinate system is the European coordinate system. Pixel size is 30 meter. And you see the bounding box. So it covers the whole of Europe, continental Europe. And it has blocks of 1,000 by 1,000 pixels. And it has overviews. It has multiple overviews, different resolutions. And it has 3 bands. Okay, so I can get all the info I need about. So, and then next thing I can go to some working directory. I would just call it under the temp. So like this. So I set the working directory, and then I can do Jiggle translate. And now imagine what I do. I create a local TIFF where I just clip Amsterdam. I know coordinates, the bounding box of Amsterdam, and I will just basically download, crop that huge image, which is 3 GB or more, and I will just crop it and get the data for where I need. Okay, just using Jiggle translate, and it will be very fast. So off we go, and we get it. We get it really in a second, right? And then we can open, I can go now to QGIS, I can freeze this one, and I can open the one that I just subset under the temp somewhere. So here's the Amsterdam file we produced. And you see it's only 3 MB. So I went from like a 3-4 GB file to produce only Amsterdam. And now it's local. Now this thing, it's local. This is really just Amsterdam. And I can just make sure I copy the style. So I can see Amsterdam. And you see there are some missing values. The missing values, but more or less I have the, so this band, which is the P50. This is hip hole. So I get that bands downloaded just for the Amsterdam. And now it's very fast, and I can load it. I can load it in QGIS or in R. I can open in R. I can do some analysis. So this is the advantage of the cloud-opted. It's super fast. You don't really have to download data to start with. You can just use the QGIS to browse the data. You have thousands of layers, so you can open layers, and eventually when you see, oh, I like this, but I need it only for Amsterdam. As you can imagine, if I had 2,000 files, I could run this Jiggle in loop, and I could crop all the files and just get the Amsterdam. And then I can load it in R, I can do analysis. And that's the advantage. And you can have 1,000 people at the same time getting the data and using it. It becomes like a geospatial database. That's really the key thing, that it becomes like a geospatial database. And I will show you that you can do also, we can do point overlays. And one of the things we can also do, we can parallelize this point overlay. So I will show you that. And I have these tutorials, including the tutorial in Open Land Map, where you do this parallelization. So maybe let me show you this thing. This is the Open Land Map. And so here under global layers, there is a nice tutorial where you can do you can test things out and, sorry, this wrong one. So here, if I do point queries, so point queries, I will just go and define that TIFF. So let me call this a TIFF. Yeah, I can do this one. So if I go back to this example, I will call an object TIFF. And then I can define here library Terra and a library Jiggle. So this one, and I can put this, for example, this Landsat image. Yes, so I defined it, and then I can say it is oops, Terra. I can say it is TIFF. Sorry. Not Amsterdam TIFF. So this is really magical now in the Terra package. You basically define the URL of the layer of the cloud.sg TIFF, and from here, this raster, it's ready for Terra package to do any spatial modeling. Although you don't have it, you don't have the data, but it's defined in the session. So it's defined and it's ready to go. So anything you do with it, it will work like the data has been loaded in the memory. You understand? So it's really magical, because I can go now to, let's see, I do this overlay. So I can, this is a single point. Let me see. If I do single point, this is a single point overlay. I just define it as a XY. And I do overlay. Now I put longitude. I have to put some longitude where I have longitude, latitude where I have values. So let me see here in QGIS. I will have to get this thing switched to coordinates to EPSG 4326, right? EPSG. So that's this one. So I switch to these coordinates, and now I look at some coordinates. So let's say 4.8, 4.81, and 52,339. 4.8. 5233. Yeah, so I define this, and now still if I overlay, I have the Latlon, but actually I did the wrong way. The layer has the projection system is this one, the European. So I did the wrong way. So sorry about that. So I have to switch back to the coordinate system, this one. No, sorry. Let's see. And that's the projection. Let's see, EPSG. I think it's 3035, yes. That's the one. And now I have to get some coordinates. And the best is, I think actually I will just, let me see if I click somewhere. And this gives me the coordinates, and I can also, well, I can copy them somehow. Can I copy them? Copy attribute value. So this was the one. So now if we do overlay, we still get, we still have missing values. Let me see. It could be. I think I have to specify this. I think maybe I have to, let me just check that, just a second. Maybe I have also wrong version of Terra. This is Y, can be matrix. Let me see if I'm mixing the X and Y. No, X and Y are correct. So this is the correct projection system. So let's see if I put here. This is the same, no difference. So I'm not getting, I should get these values 3, 4 and stuff. But for some reason, I'm getting all NAs. I'm just looking, what did I do wrong? Okay, let's try this. No. So the TIFF is defined, and I have the coordinate system. So let me just try to do this thing. Well, it's a good, it could the things don't work also. It's nice, so I can do some debugging. So just like I convert this into, so XY, and then I copy the coordinates from the intif, TIFF. Maybe this one. So let me see, now I have to see just in Terra Package, it's a bit, Robert Hammond uses different names for the projection system. How do we get projection system? Project. Yeah. Interesting, there's no way to get projection system. Let's see. How? CRS, okay. Thanks, that's the one. This one should work now. Okay, I need to put a point. So this one says, oh, I have to convert to the vector. Okay. It could be I also have to update the Terra package. No, I'm hopeless. I cannot get the values. So so let me see what they did here in this example. So this one obviously worked, but here I used the lone lot. Here I used the lone lot. And this one worked. Okay, let me, I have to dig into it. It could be that it's, I tested it with the long lot layers. So let me just test this. If this works exactly in the code, then it should be fine. This one works. And then this one I just did with like this. So I should get exactly the same as here. Yeah, this one works. So I think it's possibly this XY, when I just send the coordinates, I don't get the, I have to do the long lot. It's possible. I have to see. Maybe I have an old version of Terra Package also. But this one works. If I take another layer, let me open this layer here. This is a global layer, but we can also add it. We can add it here. Let's see. For some reason, I cannot get this one. No. I might be blocked now by Wasabi. Let's see. So I this layer I can access it through. I can access it here. So here it works. No problem. But if I want to open it in QGIS, it says not existing. That's interesting. But okay, I will check why I cannot get the EU overlay. But what is important is this thing I want to show you. If I put if I put here multiple points, so let's say I create, I don't know, 10 points. It could be 1,000 points. I could run this overlay operation in parallel. So I will take 10 cores. I don't have 10 cores, but let's say I put, or maybe I have 10 cores. I can do in parallel, and I can have a list of geotiffs, which is the list I use here. In TIFFs. Here's the list. So here's the list of geotiffs, and then list of points. So I have a list of TIFFs and list of points, and I can run this in parallel, but it says on Windows it doesn't work. So so I have to use one. But you can imagine if I have run this in the Ubuntu machine, then I can parallelize, and now it's running in parallel. Well, not in parallel this time, but you can see it's downloading. It's querying and downloading, and I can get values for all the pixels, for all the rasters. It looks like it has to download the whole tiles. I think it has to get the tiles to do an overlay. So it does take a bit of moment when I don't do in parallel, when I do this MCL apply, but not in parallel. And you know what? Let me run this. I'm experiencing some problems, so let me just run this in Ubuntu to see the difference. That will be interesting to compare. So again, the same thing. Let's run it now also in Ubuntu. We have enough memory, yes. My Ubuntu takes a lot of RAM here also, so I slowly start running out of RAM, so be careful. When it runs out of RAM, then it suffocates everything. So I think I have to stop. I will save this one. And I will turn it off. So I can save some RAM. Yes. So I'm just on the edge, but let me try to do now in RStudio. So here's the RStudio, and I run the same code with the, let's see. So I use the same code. I have multiple layers. This one works. Now I have multiple layers and I have multiple points. And now I run it using, let's say, 10 cores. Okay, so now we can compare the, this is now, so running here, see this is parallel. And the other one, it took some time to run. This should be faster. I put 10 threads, but actually I have only 6, so I should have reduced. And you see it does run in parallel, but it takes more time. I don't remember taking so much time. So I think this one went through, and this one, yeah, this one is done now. So let me just try if I put 6, because maybe having slowed it down that I put more cores. Let me try 6. So it will run the overlay in parallel for multiple points, multiple layers. And if you have like 1,000 points, as long as the points, they fall in the same, so if they're really spread equally around, it will take a lot of time. But if there's some clustering of points, it speeds it up because it only has to get this, it has to get these tiles there, whereas the values. And then it will take, yeah, it takes some time. But you could potentially do overlay without need to download with the many layers. But it does take, I see, it takes about 20 seconds. And then OV, we get this thing. We have values for the 10 points. But I downloaded lots of layers. Yeah, I have 12. So I have 12 layers, and I downloaded 10 points randomly spread. And you see the values, the difference in the values. Okay, so this is the magic of the cloud open GeoTIFFs, that you can do overlay in parallel, and you could, without downloading all the data, you can program with it. And I will do another example for Ethiopia, but for now, let me just put this on standby so I can go back here. So I'll do another example for Ethiopia. This thing. And this example I share with you also here in the, there is this soil agronomy data cube. It's a really nice tutorial also on GitLab. Let me go to that one. Solar agronomy data cube. And so here's a nice tutorial. And here we do multiple things, but basically we also use this cloud.net GeoTIFF. And then we compute, we download the multiple layers, we specify where they are, and we download these layers, load them into R, and then we can crop per farm. We can digitize in Google Earth something, then load it from KML file. Then we crop that cloud.net GeoTIFFs just for one farm. And we can also calculate for here for the Ethiopia, we can go and calculate a cropland distribution. So that's the one I will run. And I will show you then I fit a machine learning model. I take all the pixels. So that's something interesting for you. I will crop it. Then I take all the pixels and I fit a ranger model. And you see I get a model 0.92, I don't know. So it's very significant. I can see the variable importance, what's the most important, and I can then predict cropland distribution for future, assuming that the rainfall is going to fall, let's say 20%. I can make a prediction what will happen with the cropland. Of course, it drops, you know, it's like a desertification, then the croplands will drop. And so then you can compare actual cropland to potential cropland using random forest. So let me run that. I think that's a nice case study. I'll run it step by step, but you can, when you have time, you can zoom in and you can do similar things with on your own data set. So let me see, I do that here. So this is this one, building a spatial prediction model. So I start from here, I take this natural earth package and I compute, so I take this and I compute the Ethiopia because I need the boundaries of Ethiopia, right? I don't have them locally, so I can just get them from our natural earth. And then I create a raster with the Terra package, Rast. So I create for the Ethiopia bounding box, I say, make a raster at 1 kilometer resolution. And then I rasterize that. And then I can do specify these cloud alternatives that I'm interested in. They're all in our repository. So let me see, this is now, I forgot to get that package, natural earth. Install packages, and these are natural earth. See. Okay, so here's the package. And so I need the Ethiopia. There's an extra package needed. The Python people don't like this, that you have to go manually and fix, manually install packages. Let me see. Okay. I think this one is only available from, let's see. Is this available from Crown? Let me try this one. It looks like it needs this other package, not nice. 3. Okay. Okay, I made a maybe mistake. I'm running this from Windows. So this thing works. Okay, let me run this from, I will run everything from Ubuntu. That was, Lander was right. If you use Windows or something and the packages are not installed, and then you just lose time. So let's just put this in Ubuntu. Memory. Doing okay. I took on purpose the Windows machine so I can teach, because most of you are Windows. But the problem is I didn't check the packages on Windows. I forgot that in Ubuntu you just a few lines and poof. And okay, we're here. Let me start a new project. I'll just put it on the home or something. Okay. So here I just copy the whole command line and we're making our markdown. Okay. And now we can go to this one. And I go to this one. Okay, let's try now. Just switching to Ubuntu. Yeah, I can get the packages that I'm missing. So fine. Okay. See this one. Oh, it looks like this visual messed it up everything. Let's see. Okay, finally. So here in Ubuntu, I need to load Terra. And I need to load Jiggle. Okay, so project, not numeric, one more time. I didn't define it. Yeah, I forgot to define this thing. And we go here. Okay, now it's going to work. I'm sorry, some delays, but I needed to project this. And now if I project this, I get this thing. The XY. Okay, so here we create a raster, and now it's 1,200 by 1,600. That's the size of Ethiopia. We rasterize it, and then we get all the cloud optimize geotiffs. Let me see here. I convert here to raster. Ah, not F5. Okay. So now I'm trying to do this Jiggle warp. Let me see this. Okay. I put it under data. So I didn't make the folder under documents, home, Africa. So I think I need a data folder. Okay, now it's working. So now I basically create this yeah, it's a lot of warnings, but I take the African geotiffs and I aggregate them and I create them for 1 kilometer. It takes a bit of time. And I process it from the cloud optimize geotiff. This cloud optimize geotiff is 30 meter, but I don't want 30 meter, I want 1 kilometer. So I aggregate. There's a lot of these warning messages. There's something to do with Jiggle, really. I will have to read about what is it exactly saying, but I think it's looking for some metadata or something, but it's working. So I'm resampling. It takes a bit of time. So when I finish resampling, I basically have all the layers, but just for the Ethiopian bounding box, and I can also reproject them while I do Jiggle warp. And then once all these things is finished, so that's here. So this is all now finished. Now I can read it into the into R. So I actually read everything, all layers. And now I have this layer. Let's take a look at this. So now I have all the data locally on my R session, and I have about 1 million pixels, 10 layers. I have 1 million pixels. The first layer is just a mask, if it's Ethiopia or not, and the rest are just different environmental layers. So I read that, and then the next thing I can do, well, I can do just a plot. Let's see this thing. So then I get this plot, and this is like this is the cropland. This is distribution of a cropland in percent based on a global product that produces 30 meter. Okay, but I have it now at 1 kilometer. You see, it's very funny that this province in Ethiopia is probably a mountain chain, and then you don't have any cropland. Just it matches exactly the provincial boundary. But the rest is like a spread cropland. And then once we have all this data, so now we have it locally, then I load the ranger, and I say the model is, so let's see the model, the cropland is a function of soils, rainfall, elevation, so I can put all these layers. So I said the cropland is function of slope, elevation, soil pH, the cation exchange capacity of soil, and precipitation of December, January, March, September. Yes, so very simple model, right? So I said, and then when I fit the model, I have to get the complete cases, and I feed the model, and it will run. You see, it runs in parallel. It takes a bit of time, but I train that model, and as you see, then I get the model is highly significant. And then we can play with that model. We can predict, assuming, for example, that I don't know, October rainfall drops 20%, what will happen with the cropland? And so we can, once we build that model, and now this model is uses all the pixels. So there's not a based on samples. This is a fully exhaustive model. So it's a full, it takes all the combinations. There's nothing, it doesn't leave anything on accident. And you see, the ranger actually gives you estimate. It will take 2 minutes to feed this. So it takes time to feed because I use all the pixels. So it's possible, but I have 1.2 million pixels using some 10 layers. So it does take time to fit a random forest. And here I don't have to do any blocking, right? Because it's spatial exhaustive. There's no clustering, you know, all the pixels are spread exactly same same distance. And so it will take some time, and then I can go and do predictions, and that's what I showed you here, that I basically then say, let me predict now distribution of cropland if I change the, for example, the rainfall by 30% less. And then you can compare next to each other. You can see the cropland currently and cropland with 30% rainfall for 1 month, or maybe 4 months. And you can see that there will be a drop, especially here, these areas. Now lots of cropland, but here there will be less. There will still be some cropland, but it looks for this area has more effect than, for example, this area. Yes?
Where it's crop and not crop. It also predicts the range of the crop.
Percent inside 1 kilometer pixel, how much cropland? That's what it predicts. So obviously, you know, if it's 0, it means, yeah, there's no cropland, and 100% means whole pixel is cropland. So basically, it's a way to also see the effects of global warming, let's say, or global change, you know. But this is just hypothetical. I put 30% less rainfall. It will be now nice to pick up actually predicted rainfall in 10 years, predicted temperature, you know, and build this model with more covariates. But it's possible, you know. You could do this random forest exhaustively on all pixels. And you could do some ensemble machine learning also pixels. You don't have to do blocking then because they're all nicely distributed, but it's also possible to do. And then you can build these models. And you see, I'm sorry, I had some problems. I wanted to show in Windows, and that was a mistake because I missed the packages and things, because I don't use this laptop on Windows to do computing. So as soon as I switch back to Ubuntu, it ran all smooth. But this was just to show you with the cloud.NET GeoTIFF, you know, once you have a serious data, you could do local analysis, and you don't have to download data. You just use the Terra package, so you can do cropping. You can download just a piece of data. You can do overlay in parallel, so you can do lots of stuff. Sky's the limit. So and it allows you to do. You can do test analysis, and then I say, okay, I did a small area, now I want a big area, and then you can again download, just expand the bounding box. And this is all thanks to the cloud.NET GeoTIFF. So yeah, with this thing, I think I have a few more slides I want to show you. This was the example. There's one more thing to talk about, that's stack So if you're new to cloud.NG TIFF, you're also new to Stack. Stack is the way you index cloud.NG TIFF. This is at least what the OSGeo community, the people that make Jiggle, they recommend that you use Stack. And you can basically add some metadata. And then once you make a stack for your cloud solution for data, this is a cloud.NG, it's a cloud solution for geospatial data. Once you make that, there is a stack index. This one, you can send them an email that you have a data, but I think there's a way that you can yourself register, and then it becomes listed on this stack index. There's many data sets here. Becomes listed, and then people can use R stack. Also, there's a package, and then they can say, oh yeah, I need, so they will say, use a more natural language. They will say, I need data for Africa, I don't know. And then they can start programming directly. And the same things I was doing, but a bit more compact. And that way, also then in the stack, you have to put the metadata. So like now these layers, I was showing you these things. This is a bit abstract. Probably, you know, the formula I showed you, this thing. You know, when you look at these formulas, we use these long names, but you will still see, what is this? What is this layer? I don't understand. So then in the stack, you look at this metadata, and then it will tell you what's the target variable, what's the, you know, coordinate system use, who made the data, what is it for, you know? So you can all these things you get in stack, because it's like basically metadata exchange service. And so then when you program the further analysis, you know exactly which data you're using. I know it by heart because I made this data, but you haven't made it, so you wouldn't know. That's why it's important. And so that way you can do also predictive modeling, you know, and project in the future. And also very interesting way to use all the pixels. But sometimes you... Yeah, yes, but this was still with points, you know, you have to overlay the points. This model I showed you, this is something, be careful. I mean, if you have a larger data sets, you know, now I had like 1.2 million, and so when I fitted the model, it took something like 3 minutes, you know. I imagine if I took whole Africa at 1 kilometer, probably I can fit model, but it will take, then I need really high performance computing, and the model will be huge. You know, the model that I got here, M crops, let me see in the object size, it's 1.4 gigabyte. You understand? So just that model, it's 1.4 gigabyte. It's to exchange that model, just to write it on the, you know, it will take me 10, 20 seconds. So that's the thing about machine learning. Can I make this model smaller? Can I compress it? Yes, you can do feature selection. You could maybe see whether you randomly subset points and see if the model doesn't change. You know, you can compare the models. And so maybe you can do it with 10% of points, pixels, but just randomly subset. Maybe that does damage the model. So I don't know. That's something needs to be explored. Let me see, there's some questions in the chat. What's the advantages of the cloud.NG TIFF over Google Earth Engine? When data is in the Google Earth catalog, it's also kind of available to do computing. But the problem is you have to do authentication. So in the Google Earth Engine, you cannot use it without registering API and doing authentication. Now the question is whether that's open data. Is it an open data if you need to do authentication and go in some infrastructure, and you know, so if you don't have authentication, you cannot access. So then it's restricted only to people that do authentication and have the Google API. And then the question is whether that's open data. I think officially it's not open data. Open data is data which has unrestricted access. So the data I showed you, there's no authentication. We don't ask for it. You just program with it. It's a fully unrestricted access. So the European data cube we made, the Africa data, global data, it's a fully unrestricted access. You only need to have a computer to compute, but you don't have to authenticate. And with Google Earth Engine, you have to authenticate. Somebody says that my image and sound disappeared.
I was very sure, but,
Okay. Okay. Well, I hope you also, guys, that you watch online, that you saw the possibilities. There's some Q&As. I think these are all ones, so I don't have to answer this. Are there any more questions for people that are online? Questions? If you still have questions, post them via the MetaMouse, please. So just put it here in the RDev. And also I will send you this example with for Africa. So I'll just send it here. So you don't forget, this is the Africa. So you can follow things here. And with this thing, I will stop the live. Stop